Hello, I'm Noah Greer, and in this presentation, we will be going over chemical-mechanical planarization. This is the step in the chip manufacturing process that flattens silicon wafer topography so that every subsequent layer prints cleanly and will perform predictably. We'll cover what chemical-mechanical planarization is, why it's essential for process yield, the core process control knobs that are the pad, slurry, brush, and velocity, and finally, we'll cover the equipment that keeps it going in high-volume manufacturing. Chemical-mechanical planarization combines chemistry to soften or oxidize the target material and mechanical components to physically remove the material with an abrasive slurry under pressure. The goal with this process is to planarize, or to flatten the topography so that subsequent layers print uniformly and predictably. Think of it as a controlled nanoscale sanding or surface grinding, where the chemistry ensures selectivity and the mechanical components set material removal rate and flatness. In handheld tool terms, you could think of it as an extremely accurate and precise version of your handheld orbital sander. Early chemical-mechanical planarization was not focused on making the various layers that build the chip up smooth, but was simply about making the base silicon wafer surface smooth. In the 1960s, companies leaned on previous optical lens manufacturing knowledge and started tuning abrasives and chemistries for various silicon and metal surfaces. The big change came as integrated circuits started stacking more layers to keep up with Moore's law. The industry needed something better than spin-on glass and etching to get to the required performance levels. Following this need, chemical-mechanical planarization grew from a niche finishing or starting step into a tool we could tune for flatness throughout the entire process. By the late 1970s and 80s, research and development groups refined chemical slurries and process equipment to control material removal rate, surface finish, and material removal selectivity. Chemical-mechanical planarization took hold when dedicated tools, engineered pads, and application-specific slurries arrived. Shortly after that, the first commercial polishers for semiconductor chemical-mechanical planarization hit the market for high-volume manufacturing. From there, chemical-mechanical planarization became repeatable, monitorable, and scalable. When the wafer is truly flat, downstream processes become much more predictable. Lithography can be focused more precisely, so line width and depth stay consistent across the die. Film thickness and etch depth can be done more precisely. This all means fewer tweaks, reruns, and surprises later on in the manufacturing process. This inherent increase in stability keeps the lines predictable and speeds decision-making from lot to lot. The images to the right show how chemical-mechanical planarization acts as a reset for the height after each build step where it is used. Deposition, patterning, and etching create topography. If we keep going without ever having a step to reset this topography, then we risk going too far and chips will begin to have terminal manufacturing defects. Planarity impacts RC delay of interconnects and vias, which are the vertical connections shown in the image. Better thickness control reduces variation in resistance and capacitance along the conductors, which tightens timing margins and improves overall circuit performance of the chip that is being manufactured. At a high level, we tailor chemistry and pad and slurry mechanisms to the target. Copper CMP for metal levels, dielectric or oxide CMP for dielectric layers, and STI CMP for shallow trench isolation for isolating transistors on the chip. Each type of CMP balances material removal rate, material selectivity, and chip defectivity differently. For copper chemical mechanical planarization, sometimes referred to as copper damascene, The slurry typically includes an oxidizer to form a soft copper oxide, complexing agents to keep ions suspended in solution, and corrosion inhibitors to prevent pitting of the metal. Mechanically, we can tune pad hardness and pressure to limit dishing in wide copper features while still clearing the wafer. For interlayer dielectric CMP, we are flattening an oxide or low-K dielectric to hand a level surface over to the next patterning layer. Here, abrasives, often colloidal silica, dominate removal. Chemistry is typically milder, where the mechanical components do more of the flattening work. The challenge here is avoiding erosion in dense areas while achieving global planarity. Shallow trench isolation surrounds devices. Usually this will be a transistor on our chip, with the dielectric to isolate them. After filling trenches, chemical mechanical planarization removes the excess dielectric and stops on a hard mask, silicon nitride in the example shown. Selectivity and endpoint are critical to this process, as we want clean isolation without recessing the dielectric or breaking through the hard stop. Processes work to tune slurry, pad, and pressure to deliver a crisp stop with low defectivity. Now, what equipment is used in chemical mechanical polishing? You can think of these following building blocks. The polishing pad that's on the platen, a carrier head that holds and presses the wafer, a retaining ring that centers and constrains the wafer, slurry delivery to feed fresh chemistry, and a conditioning disc to keep the pad's texture stable. Each one shows up as a knob for tuning the chemical mechanical planarization process. The polishing head, also called the carrier head, is what holds and presses the wafer against the pad during polishing. It rotates, often at a different speed than the platen, and typically uses a vacuum chuck for transfer and clamping. This is the spindle that turns numbers for wafer downforce and relative velocity into actual contact mechanics at the wafer's surface. Good heads give you stable edge control and repeatable contacts. Poor compliance or drift will show up immediately as a non-uniform material removal. This is especially true at the wafer's edges. You can think of this part as the foundation for all of the chemical mechanical planarization knobs we've discussed so far and will discuss. If the polishing head isn't consistent, no slurry or pad change can fully save the uniformity. The retaining ring, shown as the green part in the sliced image, interfaces with the carrier head. It centers the wafer on the carrier and helps to control wafer contact on the polishing pad, slurry interactions, and process stability. Its material height, grooves, and wear govern edge removal and exclusion width. As rings wear, edge behavior can drift with exclusion widening or roll-off worsening, so tracking ring wear and groove integrity is part of keeping wafer-to-wafer uniformity controlled. PEEK is a material that is typically chosen for this application because of its dimensional stability, chemical resistance, low outgassing levels, and its excellent abrasion resistance. Typical PEEK retaining rings last for approximately 12 pad changes. The polishing pad is the working surface, often made of some blend of polyurethane with engineered porosity and grooves. It is what the wafer is actually pressed into to abrade the surface of that wafer. Porosity on the pad holds slurry where it's needed, while grooves distribute the chemical slurry and evacuate debris away. Pad microtexture plus slurry abrasives are used to determine how aggressive or gentle the process is at any given pressure and speed combination. Pad state changes with use. Without conditioning, pads glaze and material removal rate slows down. While on the other hand, over-conditioning can increase scratches on the wafer surface. That's why pad life, conditioning rates, and groove design matter for stable material removal rate and minimizing defects. A pad that's monitored and well characterized helps to give the manufacturer a consistent behavior from wafer to wafer. Here's an example under a scanning electron micrograph showing exactly what the pad looks like both before and after conditioning, which is a process we will touch on shortly. Something to take note of is the size variation of the holes in the pad before and after conditioning. Not understanding how the pad wears can lead to higher defect rates and a lower process yield. Shown here is a great example of non-uniformity across the polishing pad. The graph shows ultrasonic sound transmission through the pad. The numbers of the graph have been normalized, and sound transmission differences through the pad can be interpreted as differences in local densities. These differences across the pad can be one of the contributors to a lower process yield. The platen drives pad rotation and gives it a stable base to attach to. Temperature control and flatness matter. A warped platen or thermal drift will show up as a non-uniform material removal. Groove design on the pad and platen speed help balance slurry actions with mechanical contact. Chemical slurry mixture is the abrasives, usually silica or alumina, plus your chemistry, so your oxidizers, complexants, pH controllers and inhibitors, plus whatever additives for stability and foaming control is deemed necessary. Composition of this mixture is tuned to material stack to achieve the desired material removal rate, material selectivity, and defectivity. Flow rate and distribution ensure fresh slurry is at the wafer to pad's interface, and that it can carry away byproducts. Too little flow will starve the interface, while too much wastes consumables. Uniform dispensing of the slurry across the pad radius can help uniformity. Slurry filtration is a critical part of the slurry delivery process. The graph on the left is a copper surface that was polished with an unfiltered slurry. The graph on the right is a different copper surface that was polished with a filtered slurry. The results from the filtered slurry mixture are significantly better than the unfiltered slurry, with a noticeably lower defect rate. Filter selection itself is a critical part of the process. This is where things like pore size to bound slurry particle size, flow rates, pressure drops, and chemical compatibility all need to be taken into account to choose the right tool for the specific job. Conditioning retextures the pad with a diamond disc so that it can continue cutting consistently. Without it, the pad clogs, glazing over with slurry residue. This results in a lower material removal rate. Overconditioning, on the other hand, can raise scratch risk. Pad conditioning comes down to a balance between pressure and speed. The key levers here are your disc type, grit, downforce, sweep pattern, and frequency. Oftentimes, the pad needs reconditioning between wafers, and sometimes in process during the actual polishing step. The goal here is a stable, repeatable pad state from wafer to wafer. Immediately after polish, we need to remove particles, metal ions, and slurry films. Brush boxes, megasonic stages, and the high purity deionized water rinses, followed by a drying step, are typical of this process. Good cleaning prevents redeposition and corrosion, which protects yield. To bring it all together, here we have a simple four-step example. Interlayer dielectric CMP is used to level a dielectric. Then metal patterning and etch is used for creating features. Then a copper deposit is used to fill them. And then finally, a copper CMP is used to clear the excess copper and leave metal only in the trenches and vias. This process will repeat multiple times, so the consistency of each CMP pass really matters to the whole chip building process. Common defects we can encounter are scratches, residues, corrosion and pitting, dishing and erosion, and particles left behind on the surface. Mitigations can include using the correct abrasive size, proper inhibitor balance, proper pad conditioning, using an optimized rinse process, and a robust post-CMP cleaning process. Shown here is a good example of how varied the material removal can be depending on the geometry that is being abraded away. The feature-dense area has increased erosion when compared to the non-feature-dense area, and dishing can be seen in both areas. On the process and material side, chemical mechanical planarization often hits a narrow operating window because we're polishing multiple materials at once. This is typically copper alongside a hard dielectric oxide, so the slurry chemistry and pad downforce have to be tuned for both materials at the same time. The use of ultra-low K dielectrics also add risk. They're mechanically fragile, so it's easier to delaminate or fracture if the process is too aggressive. Endpoint is another challenge. Knowing exactly when you've reached target film thickness can be non-trivial without strong in-process monitoring signals or tight model-based timing. Some of these signals would be things like the current going into the motor or the condition of the slurry mixture that's leaving the pad. And finally, your consumables. Your pads, conditioners, slurry, and their waste handling can be a cost driver. So disciplined change control and disposal processes are needed to keep cost and compliance within spec. To wrap it up, your main knobs are pad type and age, slurry composition and flow, carrier downforce, relative speeds of your platen versus your carrier, your pad conditioning rate, temperatures, and finally time. And all of these interact with each other. For example, a fresher pad cuts faster, but can raise scratches if slurry abrasives are aggressive. So it all needs tuning. Your material removal rate scales with pressure and velocity, and this is modulated by chemistry and pad microtexture. Selectivity is important, so that is your target versus stop layer and what you're actually trying to polish away. Uniformity is going to be driven by your carrier head and pressure control, slurry distribution, pad grooves, and feature density on your specific wafer. Pattern effects like dishing and wide metal and erosion in dense areas are managed with design fill, zoning, and correct pad and slurry selection. Chemical mechanical planarization performance is at its roots a systems problem: pad, slurry, mechanics, and target pattern. Tight control over consumables, conditioning, and endpoint helps to deliver planarity with low defects. In the end, manufacturers are aiming for rates that are fast enough for throughput, but gentle enough to protect today's complicated geometries.